So let's dive into these mandatory levels and show you why each one of these is important in severe weather forecasting and what you should be looking for when you're analyzing these upper air maps during a severe weather forecast. Let's start off with perhaps our most important mandatory level, 500 millibars. Most forecasters use a top-down approach to forecast severe weather where they start with the highest level of the atmosphere and go all the way down to the bottom in succession. I like to start at 500 millibars because it really gives us a good idea of the overall background pattern, and we can make a lot of assumptions just by looking at the 500 millibar map. First, let's just give you a brief overview of what all of these symbols and lines mean. Basically, these blue barbs here, these are wind barbs. So basically it tells us the speed and direction of the wind. These barbs consist of flags, full staffs, and half staffs. Each flag is worth 50 knots. The winds in the upper levels of the atmosphere are measured in knots. The full staffs are worth 10 knots, and the half staffs are worth 5 knots. So in this example here, this would be a 50 plus 10 plus 5 knot wind, which is a 65 knot wind. And the direction of the wind is assumed by going through the flags and staffs toward the end of the barb, or toward the center of the station. So this would be a 65 knot wind out of the southwest. So that's how those wind barbs work. These lines here, these solid black lines, are not pressure contours. They are contours of equal geopotential height. Let me explain what geopotential height is. Recall that all of these individual weather maps in the upper levels of the atmosphere, each mandatory level, is a constant pressure surface. So it's basically a surface where the pressure is the exact same across every point on that surface. So for example, on the 500 millibar map, every point on this map is at 500 millibars. So we can't really use pressure to determine areas of high and low pressure like we would at the surface. We'll talk about the surface map here in just a bit. So we have to use a variable called geopotential height. Geopotential height is the height of a constant pressure surface above mean sea level. And geopotential height varies based on variables such as temperature. So in some locations, the 500 millibar surface, for example, would be lower than it is at other locations. As you can see here, the height actually varies across the entire 500 millibar constant pressure surface. This is what geopotential height is, and this is how we can measure how changes in the atmosphere are occurring on these constant pressure surfaces. On the 500 millibar map, we're really looking for features called troughs, and troughs are these downward bends or downward kinks in the geopotential height contours. So you see here that the geopotential height contours are kind of bent like a ski jump or a skate ramp. And so that's how you can think of these troughs. It's just like a skating ramp. The winds go through the ramp, they accelerate toward the base of the ramp, and then they eject into the other side of the trough, other side of the ski jump. And that other side of the ski jump is where you want to be for your highest chance of robust severe weather. That is called the exit region of the trough. So if we were to draw an axis from the center of the trough through the base of the trough, so basically through the base of the ski jump, we would want to be on the right side of the axis. So all this area over here on the right side of the axis is the exit region of the trough. And the exit region of the trough is the most favored area within the trough for upward motion or lift. Lift is maximized in the exit region of the trough. Lift is one of our most important ingredients for severe weather. And again, in the exit region of these troughs, that's where lift is maximized. And so the exit region of these troughs is where the chances for severe storm initiation is greatest because the lift is maximized in that portion of the trough.
Storm chasing is hard. Get expert help from a live coach. Discord community link in description.
Now, which way the trough is oriented is also important. What happens in the mid and upper levels of the atmosphere, 500 millibars is considered the mid levels of the atmosphere. What happens at these levels dictates what happens in the low levels of the atmosphere, and the orientation and geometry of troughs can give us an idea of how robust the response is going to be at the low levels, because whatever happens in the mid and upper levels of the atmosphere dictates what happens in the lower levels of the atmosphere. So going back to our trough axis here, this dashed pink line basically through the center of the trough down through the base of the quote-unquote ski jump. When this axis is tilted back to the left, like it is here, this is called a negatively tilted trough. Negatively tilted troughs tend to produce a more intense low-level response, which means a more intense surface low or low-level cyclone development. Again, we'll talk about the low levels here in just a bit and the surface here in just a bit. But these troughs tend to induce surface low development, especially when they go over the higher terrain areas like the Rockies. So when these strong winds go through the base of the trough and go over the higher terrain of the Rockies, they tend to induce surface low development, surface low pressure development. When you have a negatively tilted trough, that surface low pressure development tends to be more intense than a positively tilted trough, which is when the axis tilts toward the right. So in this example here, we have a very robust trough across the western U.S. Its axis here goes from basically northern Nevada down through the desert southwest into western Mexico. It's tilted back toward the left, so this would be a negatively tilted trough. So we would expect, as this trough moves into the central U.S., that we would see pretty robust surface cyclone and a low-level cyclone, low-pressure development in the low levels here in the exit region of that trough. And low-pressure development tends to occur in the exit region of these troughs. So to summarize, at 500 millibars, we want to be looking for these troughs in the geopotential height contours, and we want to focus on the exit region of these troughs for the greatest chance for severe storm initiation, because lift is maximized in the exit region of these troughs.
Remember to check out those links in the description below, and then watch another video.